A machine in the mountains of Chile just woke up. Not a weapon, not a defense system. Something far more dangerous. A witness. For the next 10 years, it will watch. Every 3 nights, it will scan the entire southern sky, documenting everything that moves, changes, or dies. Every single night, it will generate 10 million alerts, millions of cosmic anomalies, astronomical events, and patterns humans have never seen before, streaming in real time to laboratories across the world. What most intelligence agencies already understand is what the public is only beginning to realize: this is not astronomy. This is surveillance on a scale that dwarfs any human capability. And the data it's collecting right now is already rewriting what we thought we knew about the universe itself. The first images arrived on a Tuesday morning in June. Not slowly, all at once. Hundreds of photographs, each one a composite of multiple observations, each one revealing details of the universe that no human had ever seen before. The Vera Rubin Observatory, perched at 2,682 meters on Cerro Pachon in Chile, had opened its eye. And what it saw in just over 10 hours of observation challenged everything we believed we understood about cosmic scale, detection capability, and the future of how humanity monitors the heavens. But here's what nobody publicly discussed in those first moments of celebration. The implications were already reshaping intelligence frameworks, astronomical institutions, and the fundamental assumptions about what observation truly means in the modern era. Think about this carefully. What would it mean if a single instrument, one telescope, one camera, could discover more asteroids in 10 hours than the entire global network of every other observatory combined detects in an entire year? That is not speculation. In approximately 10 hours of test observations, the Vera Rubin Observatory discovered 2,104 never-before-seen asteroids in our solar system, including 7 near-Earth asteroids. By comparison, all other ground and space-based observatories combined discover approximately 20,000 asteroids annually. Within the first 2 years of full operations, Rubin alone will discover millions of new asteroids. Read that again? Millions. Not thousands. Millions. The discovery rate is not incremental. It is exponential. It is categorical. It represents a fundamental shift in humanity's ability to detect and track objects moving through the darkness. But this is where the narrative most mainstream outlets missed the actual story. The asteroids were never the real objective. They were the appetizer, the proof of concept, the demonstration of capability. What Rubin was actually built to do, what it is doing right now, every single night from that Chilean mountaintop, operates on a far deeper, more consequential level. The observatory's processing systems will detect millions of changing objects, literally every night. Each night, the observatory generates around 20 terabytes of data, processed through computer algorithms that flag any patterns or rare events in particular patches of sky over time. Let's establish the scale: 20 terabytes every night. To contextualize that number, the entire Library of Congress contains approximately 17 terabytes of data. This machine generates more information in a single evening than one of humanity's greatest knowledge repositories holds in total. And it does this automatically, relentlessly, every night for 10 years. And this is where everything changes. The Vera Rubin Observatory officially began the Legacy Survey of Space and Time, the LSST, in late 2025, following an operational readiness review and the beginning of the alert stream. Over the next 10 years, Rubin will relentlessly observe the entire southern sky every few nights to create an ultra-wide, ultra-high-definition time-lapse record of the universe. But the word survey masks the true nature of what is happening. This is not passive observation. This is not a research project conducted at leisure. This is continuous, systematic, automated surveillance of half the sky, every 3 days, without exception, for the entire next decade. And when something changes, when something moves, when something appears or disappears, the system doesn't wait for human authorization. Each night, Rubin collects approximately 10 terabytes of data and produces as many as 7 million alerts of changes in the night sky. These alerts stream to alert brokers, automated systems, that sort and classify these changes so scientists can act quickly. 7 million alerts per night. Think about what that means operationally. Think about what it means politically. Think about what it means for the institutions and governments trying to interpret this unending cascade of cosmic information. According to informed sources familiar with the observatory's capabilities, what most people are not seeing is that Rubin represents the first truly comprehensive, real-time surveillance system for the entire observable universe, accessible from Earth. Every transient event, supernovae, explosions, billions of light years away, asteroids, tumbling through the solar system, gravitational waves translated into electromagnetic signals, all of it gets detected, cataloged, and broadcast simultaneously to competing international research networks, government agencies, and institutions whose interests do not always align. This is not chaos disguised as science. This is strategy disguised as astronomy. The control of who sees what first, who interprets what means what, and who acts on which alerts carries enormous geopolitical weight that remains largely invisible in public discourse. The real power, though, resides in what happens when you combine Rubin's unprecedented discovery capability with the actual scientific missions driving the observatory's construction. Everything we know, galaxies, stars, planets, all ordinary matter, makes up just 5% of the universe. The remaining 95% is made up of dark energy, 68%, and dark matter, 27%. Rubin Observatory will help scientists map the large-scale structure of the universe with finer observation. Dark energy, accounting for 68% of the cosmos, actively accelerates the expansion of reality itself. Yet we cannot touch it, measure it directly, or even truly understand what it is. Measuring distances across the universe is a fundamental challenge, and Rubin's rapid scanning will capture the largest sample of type Ia supernovae yet, unlocking new insights into dark energy's effect on the universe's expansion. Over its 10-year mission, Rubin could fundamentally change our understanding of how and when the universe formed, and this is where the psychological weight of the moment becomes apparent. Rubin is not just cataloging the universe, it is being specifically weaponized, in purely scientific terms, but weaponized nonetheless, to finally answer the largest remaining questions about fundamental reality. The Vera Rubin Observatory will enable precision measurements of the growth of structure across cosmic time, studies of dark matter in the cosmic context, and investigations into the nature of dark energy parameterized through fundamental cosmological equations. Every night, for 10 years, this machine will gather evidence about the composition, structure, and evolution of reality itself. What it discovers about dark matter's distribution could reshape our understanding of galactic formation. What it reveals about dark energy's behavior could overturn fundamental assumptions about whether the universe's expansion is constant, accelerating, or behaving in patterns we have not yet predicted. But the real story goes deeper still, because Rubin is not operating in isolation. Other observatories like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, have similar plans to measure cosmic expansion and chart large-scale dark matter distributions. Multiple institutions are racing to answer these same questions simultaneously. This is competition dressed in the language of cooperation, different nations, different scientific institutions, different teams all operating their own instruments, all collecting their own data, all trying to be first to solve the universe's greatest mysteries. The geopolitical implications are substantial. Control over the interpretation of dark energy's behavior translates to control over our understanding of cosmic destiny. Precedence in mapping dark matter distributions establishes intellectual authority over fundamental physics for decades to come. Now examine what exists at the intersection of these two capabilities: detection and interpretation. Rubin's images reveal everything from violent cosmic collisions to faraway nebulas. The Virgo cluster images show the chaotic jumble of merging galaxies, a process playing a crucial role in galaxy evolution. The level of detail from large-scale merging galaxies to spiral structures of individual galaxies, to distant background galaxies, to foreground Milky Way stars, all appears in single images, which is transformative for astronomical research. Every detail matters, because every detail contributes to the comprehensive model. And that model, when complete after 10 years, will represent the most detailed map of cosmic reality ever constructed. It will show us where dark matter concentrates. It will show us how galaxies collide, merge, and evolve. It will show us the universe not as a static backdrop, but as an active, changing, dynamic system where events unfold and objects move and relationships shift. What transforms this from impressive science into something more significant is the real-time component. The LSST will eventually produce 10 million alerts per night. Whenever an asteroid streaks by, a star explodes, or a distant object brightens or fades, Rubin will issue an alert in little more than a minute, so astronomers can rapidly follow up with other telescopes. Researchers will stack years of images to create deep, detailed cosmic maps of 200 million stars in and around the Milky Way and 20 billion distant galaxies. Stop here. 1 minute. That is the latency between detection and alert transmission. Across international networks, different time zones, competing institutions, and geographically dispersed research teams, the observatory can identify, process, and communicate significant cosmic events within 60 seconds. The first institution to act on an alert has enormous research advantage. The first network to interpret an anomaly establishes interpretive authority. The first team to understand a novel phenomenon gets to name it, explain it, and guide how the rest of science interprets it. This is not theoretical anymore. The systems are running. Astronomers have already used Rubin's public alerts to discover and follow up hundreds of transient phenomena during the early optimization period, demonstrating that the alert pipeline works and that the global astronomical community can organize rapid follow-up observations. Real discoveries are happening right now. Real asteroids are being tracked. Real supernovae are being observed. Real data is flowing from Chile to laboratories worldwide every single night, and the race to interpret it, to understand it first, to establish scientific priority and authority, is actively unfolding as these words are being read. But here is where the full geopolitical architecture becomes visible. The Vera Rubin Observatory is a U.S. government facility. It is jointly funded by the U.S. National Science Foundation and the U.S. Department of Energy's Office of Science, operated through NSF NOIR Lab and DOE's SLAC National Accelerator Laboratory. Think about that institutional structure. Not just science, not just academic research. The Department of Energy, the same institution that oversees nuclear weapons, particle physics, and fundamental research into the nature of matter. When the Department of Energy funds an observatory specifically designed to understand dark matter and dark energy, the forces that comprise 95% of the universe, that is not a casual research investment. That represents a strategic decision to position the United States at the absolute forefront of understanding cosmic reality. And the data, all of it, flows first to American institutions. According to informed sources in the astronomical community, the first images were released to the public, but the data processing pipeline is based at SLAC National Accelerator Laboratory in California, with alert generation and distribution handled through American systems and institutions before being shared with the broader international scientific community. There is a temporal advantage in having your systems process the data first. There is an interpretive advantage in controlling the infrastructure. There is a strategic advantage in understanding the cosmos before competitors can fully analyze the same observations. Every advantage compounds. Every early discovery establishes momentum. Every first interpretation guides how subsequent observers understand what they are seeing. The implications ripple outward in patterns most discussions ignore. The Vera Rubin Observatory officially began its legacy survey of space and time on schedule, capturing hundreds of images each night to enable discoveries related to dark matter, dark energy, supernova, and near-Earth asteroids. The decade-long survey creates the most comprehensive record of the universe in history, combining immense field of view with depth and speed to detect extremely faint objects. Extremely faint objects. Objects at the edge of detectability. Objects that only become visible when you have a camera sensitive enough, a telescope powerful enough, and a data system sophisticated enough to extract signal from noise. This is where the machinery of modern astronomy meets genuine discovery. Rubin doesn't just see what was previously known, it reveals what was previously invisible. The philosophical weight here warrants examination. For the entire history of human civilization, the universe was fundamentally unknowable beyond its visible surface. We could see stars and planets and moons. We could measure their positions. We could track their movements. But we could not see the vast majority of what actually exists. We could not see dark matter's gravitational scaffolding holding galaxies together. We could not see dark energy's relentless pressure expanding the cosmos. We existed in a kind of cosmic blindness, able to perceive only 5% of reality. And now, through a machine built by the United States government and deployed on a Chilean mountaintop, we are finally acquiring the instruments to pierce that blindness, not completely, but substantively. And that acquisition of knowledge, that shift from ignorance to understanding, transforms who holds power in the conversation about cosmic destiny. But here is where the story becomes unsettling. Because dark matter and dark energy are not purely academic concerns. They determine the ultimate fate of the universe. Studies of dark energy's nature and behavior will allow calculation of whether the universe's expansion accelerates eternally, whether it reaches an equilibrium, or whether it reverses into contraction. Type Ia supernovae observations provide the data needed to measure this expansion rate and potentially reveal whether dark energy's properties evolve over time, something that would fundamentally challenge current cosmological models. We are talking about the end of everything, the fate of galaxies, stars, planets, and all possible futures. And we are now constructing instruments specifically to understand the forces determining that fate. And the first nation to truly understand those forces, to possess actionable knowledge about cosmic destiny, holds a form of intellectual authority that transcends traditional measures of power. The European Space Agency understands this. China understands this. Russia, despite economic constraints, understands this. India, with its growing astronomical capabilities, understands this. The fundamental struggle in 21st century science is not for marginal improvements in understanding. It is for precedence in answering the greatest. The Vera Rubin Observatory's primary science goal is constraining dark energy through weak gravitational lensing of large-scale structure. After a full year of data from LSST, These measurements will reach precision comparable to recent dark energy spectroscopic surveys, providing an independent test of hints that dark energy may evolve over time in ways current models do not predict. Evolve. That is the word that should trigger attention. If dark energy's properties are not constant, but instead change over cosmic time, that overturns fundamental assumptions about the universe's behavior, that requires rewriting physics textbooks, that establishes the team that first detects this evolution as the authority on cosmic physics for the next generation. And the observable period is extraordinarily narrow. The 10-year survey window creates a specific temporal frame for observation. Observable universe data collected during this decade will become the baseline against which all future cosmic observations are compared, establishing the reference model for cosmic behavior and dark matter. Distribution that will guide research and interpretation for potentially centuries. This is not indefinite. This is 10 specific years during which the southern sky will be continuously mapped with unprecedented precision. The data collected during this window will define how we understand the universe from this point forward. Every discovery made, every pattern identified, every anomaly detected becomes part of the permanent record of cosmic reality. Now contemplate what happens when the 10-year survey concludes. What happens when the machine on the Chilean mountaintop finally falls silent? Rubin will eventually stack years of images into comprehensive cosmic maps, showing billions of objects with unprecedented precision. The resulting model will establish the definitive three-dimensional map of dark matter distribution across billions of light years, the temporal record of cosmic expansion's acceleration, and the baseline against which all future astronomical observations will be measured. That map does not go away. That data does not disappear. That archive becomes the foundation for every subsequent astronomical discovery. Institutions without access to superior instruments will use Rubin's data for decades. The United States' scientific institutions will have priority in interpreting that data first. The research programs built on Rubin's discoveries will establish American scientific authority across cosmology, astrophysics, and fundamental physics for the foreseeable future. But what if the discoveries are not what we expect? What if dark matter behaves differently than theory predicts? What if dark energy is not accelerating uniformly? What if the universe's structure contains anomalies that current models cannot explain? During optimization observations, Rubin has already detected phenomena during follow-up of gravitational wave alerts, suggesting the observatory can rapidly respond to unexpected cosmic events and detect electromagnetic counterparts to gravitational disturbances with unprecedented precision. Unexpected phenomena, novel events, gravitational signatures that had no previously observed counterparts. The machinery is already detecting things we did not know existed. The 10-year survey will undoubtedly reveal patterns, structures, and events that contradict current understanding. This is where scientific discovery transitions into something more consequential. The institutions controlling the first interpretation of unexpected cosmic phenomena establish paradigmatic authority. They get to decide what the anomalies mean. They get to guide how the broader scientific community understands the discoveries. They get to shape the narrative about what the universe actually is, beneath the visible surface, in the domains of dark matter and dark energy, where fundamental reality operates according to rules we are only now beginning to comprehend. And the data continues to flow, night after night, alert after alert. 7 million cosmic events reported every single night. The Vera Rubin Observatory has officially begun operations as scheduled, with hundreds of images captured nightly and the alert system distributing millions of notifications to automated brokers and research institutions worldwide. Millions, every night, for 10 years. That is not a research project. That is a surveillance system of cosmic proportions, watching the entire southern sky continuously, detecting everything that moves, changes, or appears, and broadcasting that information in real time to institutions that must interpret it, understand it, and act on it within minutes. The question that should be haunting us now is simple. What happens when the survey ends? What happens to the observatories built after Rubin? What happens to the international race to understand dark matter and dark energy once this decade of continuous observation concludes? Will the advantage gained by the United States, scientific institutions, remain insurmountable? Or will competing nations and research programs catch up, develop their own superior instruments, and challenge the interpretations established by Rubin's data? Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will also measure dark matter distribution and cosmic expansion. Multiple observatories operating simultaneously will provide independent verification of cosmological measurements, but also create competition for research priority and discovery credit. The race is accelerating. The stakes are becoming clearer. And every night, from a mountaintop in Chile, a machine with the largest digital camera ever built opens its eye on half the sky, watching, measuring, detecting, and reporting everything it sees. What it has already discovered is rewriting astronomy. What it will discover over the next 10 years will transform our understanding of fundamental reality. And who interprets those discoveries first? Who establishes authority over their meaning? Who shapes how humanity understands the dark matter and dark energy that comprise 95% of everything that exists? That is a question that will define the next era of cosmic science, scientific authority, and the geopolitical struggle for intellectual dominance in understanding the nature of reality itself. The observatory is watching. The data is flowing, and the implications are only beginning to become visible.